welcome back, everybody. So for our second talk of the morning, we are very excited to have Peter Manohar from CMU to tell us about an exponential lower bound for linear three-query locally correctable codes.
Based on two papers that are both joint work with my advisor, Pravesh, who was at CMU and has now moved to IIS in Princeton. So I'm going to start off the talk by just defining locally correctable codes. So we've seen this definition a couple of times yesterday, but seeing it one more time isn't going to hurt you. Okay, this is going to be a code. I'll take a k-bit message and code it into an n-bit string. For this talk, all my codes will be systematic, meaning that the first k bits of this encoding are indeed equal to the message b. And then we're going to allow an adversary to come in and make an arbitrary delta n corruptions, which will give us some string y. And then we want this to have a local decoder, meaning there should be some algorithm that takes as input an index u, which is specifying the bit of x that we would like to recover. And then the decoder gets to toss some coins and read at most q entries of y, potentially adaptively. And then it should output some estimate x hat sub u, and hopefully this is equal to x sub u. And we'll just say that this code is q delta epsilon locally correctable if, when y is within distance delta from x, and for any u, the decoder will read at most q bits of y and nonetheless recover x sub u with probability at least 1 minus epsilon. And so because you guys are all coding theory people, I probably don't need to convince you that these codes are very useful. You've probably seen their applications in things like probabilistic checkable proofs or private information retrieval schemes and so on. So I'm not going to motivate these that much, but I mean, we've seen a few talks on these works. So it's hard to talk about locally correctable codes without talking about locally decodable codes, which are a very closely related notion. And the real only difference is in a locally decodable code, I just want to recover a bit b sub I of the message rather than any bit x sub u of the encoding. So it's a weaker notion because I assume the code is systematic, so that means if I'm locally correcting any bit of the encoding, I'm in particular locally correcting these bits here, which is the message b. Okay? So I can just kind of toggle back and forth, but you can see that the real difference is whether I'm decoding an I in k or a u in n. Okay. All right, so the first question I want to ask is, do these codes exist? And as we'll see, and I mean, you should assume, given the fact that I'm talking about this subject, that these codes are indeed going to exist. But I want to point out something here, which is that this is a purely combinatorial question. We do not care at all about efficiency or like efficiency of encoding and things like this, or explicit constructions. I just need an existence proof. And the reason can't use, say, standard random coding arguments is because there's no natural probabilistic model from which we can sample these objects. So unlike, say, Shannon's random coding argument that lets us show that there exist good codes, we cannot do something like this here, or at the very least, we don't know how. But these codes do exist, and there's a very simple way to construct them, which is the Reed-Muller code. And this gives you a q-query locally correctable code. And the block length of the code is exponential in k, so it's 2 to the k to the 1 over q minus 1. And it's also a q-query locally decodable code because it's an LCC. And so let me just go through this construction very quickly for 3 queries. What you do is you take degree 2 polynomials over a field f4, and you look at their evaluations over all points in f4 to the t, where they're in t variables. And the way you decode f of z is you simply pass a random line through z, and then you read the 3 other points on the line. And because this is a degree 2 polynomial, this lets you interpolate and therefore recover z. Okay. And you can get a binary code by just projecting this down to f2 via the trace map. And it has some parameters if you compute them. The block length is 2 to the order square root k, but more explicitly, the constant is 2 root 2. And so this is a very simple code. If you hadn't seen locally correctable codes before, but you knew some coding theory, this might even be the first thing you would come up with. It's kind of the first natural object to try. But what I want to ask now is, can we do better? I mean, if this is the first thing we're trying, then perhaps you could imagine that some more complicated algebraic techniques will indeed yield better codes. So let me tell you the story of what we knew in 2022, just as little as 2 years ago. So we'll just turn the clock back just 2 years, and let me tell you all our knowledge from 2022. This was the knowledge, the state of the art, when we had this very nice coding theory workshop at Stock 2022. And Shubhangi, I think, gave a talk on pretty much all of this stuff in the workshop. And yeah, so for q equals 2, we know that the Reed-Muller codes, which gives you the Hadamard code in this case, has a block length that's 2 to the k. It's a 2-query locally correctable code. And in fact, this is tight. So even though this is a pretty bad code, you can't do any better because there's some works in the early 2000s on proving 2-query lower bounds for locally decodable codes. And so it's even for the weaker notion of local decodability that we also have this exponential lower bound. And for q equals 3, as I said, linear 3 LCC, the Reed-Muller code is a linear 3 LCC that gets a block length n that's 2 to the 2 square root 2k. But something very interesting happens at 3 queries, which is for locally decodable codes, there exist better constructions. Namely, comes from 2 works of Sergei Yakanin and Klim Efremenko that show the existence of a linear 3-query locally decodable code of subexponential length. In particular, if you look at this exponent, it's like a 2 to the order square root k, and a polynomial exponent would be like 2 to the order log k. So this is, in particular, sub-polynomial here in the exponent, and therefore sub-exponential. And you can ask if this code, which is substantially better than Reed-Muller, is actually locally correctable. And the answer is we actually don't know. So it's probably believed that it's not locally correctable, given that when you construct these codes, usually you get sort of local decodability or correctability for free by the way you've constructed the codes. And these codes do not have an obvious local correction algorithm, so you should probably assume that there just isn't one. But formally speaking, we haven't been able to show this, even for like this very explicit, specific code. And if you're wondering whether any of these are close to optimal, the answer is we really don't know either. Our best lower bound is this very weak k-squared lower bound for 3-query locally decodable codes. And this comes from the same work of Carnegie and de Wolf. And in fact, there's even some amount of formal evidence that our techniques can't go beyond this k-squared. So there's been these 2 works that are trying to formalize somehow the arguments we're making in these lower bound techniques and just trying to argue that these arguments cannot go better than k-squared. So just to summarize, I asked, can we do better? And the answer is yes for LDCs, and for LCCs, we don't know. And given that we've been perhaps trying to construct better locally correctable codes for quite some time, at this point you might say, maybe we're not doing better because Reed-Muller codes are actually optimal. And we know that this is true actually for 2 queries. And for 3 queries, this is pretty much wide open. And there's this very interesting paper of Barkoli, Shai, and Weinreb that showed this connection between this statement and a conjecture in design theory of Hamada that informally says that Reed-Muller codes are optimal designs, where a design is like a specific type of locally correctable code with some additional nice structure. I'm not really going to get into the formal definition of a design, but you can imagine it's just like a nicer, even cleaner version of an LCC. And the thing is, if we want to try to prove either of these, there's a very big technical barrier in all our techniques, which is that all our lower bound techniques actually apply to locally decodable codes, the weaker object, not just locally correctable codes. And remember I said matching vector codes are 3-query locally decodable codes of a block length much better than Reed-Muller. So in particular, if we're only proving lower bounds for locally decodable codes, we cannot get either of these 2 statements. So far, so good? Okay. So now let's flash forward to 2024, the present day, and let me tell you what we know now. So I'm going to plot the results that we have on this graph, where here I have the k-squared, the best lower bound, and 2 to the 2 square root 2k, the best upper bound that we knew in 2022. And here we have this LDC barrier. This is the barrier that you cannot surpass if you're only proving lower bounds for locally decodable codes. And this is the k-squared barrier, where we have some evidence that our techniques are not even able to go beyond this bound. So in a first work with Omar, who is, there he is, hello, and Venkat, Venkat's over there, hi Venkat, and Pravesh and myself, we showed that 3-query locally decodable codes have a block length that's k-cubed. So in particular, this is above this k-squared. And this is a modest improvement. At least we got past k-squared, but we're still pretty far from this upper bound, and we're in particular not even close to this LDC barrier either. And then late last year, Pravesh and I showed that for at least linear 3-query locally correctable codes, we prove a lower bound of n is at least 2 to the k to the 1/8, which lies here. So this is above the LDC barrier. And I want to point out a few things about this. The first is that our strategy does not work for locally decodable codes. And this is inherent because if we're proving a lower bound above this barrier, we have to do something different. In fact, this is essentially the first lower bound for either locally decodable codes or locally correctable codes that does something different than in the locally decodable case. So the typical way we've been proving lower bounds for LCCs has just been saying, oh, it's an LDC, we're going to give up on the LCC property and go from there. And so this is the first time we've really done something substantially different for an LCC. And as a byproduct, we've proven that these matching vector codes are indeed not locally correctable. And then, so this was, we posted this in about November, and then, well, in February, Tal, I don't see him, oh, there he is. Yeah, so Tal Yankovitz had this very nice work where he essentially followed the same proof strategy, but it injected some very cool, clever new ideas to get this up to a k to the 1/4, which is now getting really close to the square root. And then as Omar told you yesterday, very, very recently, him and Venkat got a lower bound that gets up to 2 to the square root k over log k, which is like very, very close to optimal now. And so the approach of this work of Omar and Venkat actually follows a slightly different approach. I mean, the core technical idea is still sort of the same, but their execution of the proof is quite substantially different, I would say. So they explore this connection between rainbow cycles and LDC lower bounds. This is something that was somewhat implicit in our work on LDC lower bounds here, and something that was made explicit in this work of Shea, Kotari, Mohanty, Munha, and Sudakov. And what they do is they're able to get this very short, as Omar said yesterday in his lightning talk, a 2-page reduction. It's very, very nice to this rainbow cycle bound, which is a problem that's been studied in combinatorics quite extensively. And there was a recent breakthrough in September of last year by Alon Bucic, Zauerman, Zakharov, and Zamir that gets a very, very almost optimal bound for the rainbow cycle, which they make use of to get this near optimal bound here. And in retrospect, if you view our proof through this rainbow cycle lens, we're showing the existence of some weaker form of a rainbow cycle. It's not quite the same type of cycle that's being found by this theorem. And many of the technical complications in our proof are actually because we're essentially reproving some weaker form of this combinatorial statement here. And concurrently with this paper, Pravesh and I proved that for design 3 LCCs, we get a lower bound that's 2 to the 1 minus little o of 1 times root k. So basically up to this very small little o of 1 factor, we get a 2 to the root k bound. That's like there's no hidden constant there at all. And as you can see down here, this is, up to this 2 root 2 factor, this is really, really close to tight. And this in particular proves this Hamada's conjecture for 4 designs up to this 2 root 2 factor. And there's something interesting that I want to point out here, because I said that we were proving some weaker form of a rainbow cycle. And this work of ABSZZ has a pretty long discussion where they show that their techniques cannot get rid of the extra loss that is incurring this log k factor loss here. And moreover, they actually have some heuristic sorts of arguments, and they're sort of speculating that perhaps this is actually the correct bound for the rainbow cycle problem, and you can't even get rid of this factor. And so there's something interesting going on here where if this speculation is in fact true, this means that the fact that here we're proving some sort of weaker bound, some weaker version of a rainbow cycle and not the full strong statement here is maybe what you actually would need to do to get all the way up to root k. But this is all speculation. So this is, I guess I feel comfortable saying it because it's the work here it's their own work that speculates, so I'm not doing it myself, but we don't know yet. So this is something very interesting to investigate. Yeah.
Just to clarify, the 2 follow-ups by Yankovitch and Al-Rabi-Gosrami, those also just apply to linear?
They're also for linear. This is all for linear. Yeah, so this is actually my next point is all these lower bounds, while they're very, very nice, are only for linear codes. And so that means our best lower bound is still this k cubed if we go to nonlinear. And that's, maybe I might want to see if all these ideas, we have a now big wealth of new ideas, see if they can get better for nonlinear. And in the same paper, Pravesh and I prove a much better lower bound for nonlinear codes. It's k to the 1 over 2 epsilon, where epsilon is this decoding error parameter. So in particular, if epsilon is like a small constant, like 1 over 100, we're far surpassing this cubic bound. And as epsilon goes to 0, we can get this all the way up to something super polynomial. All the results clear? I know it's like a lot of things to throw at you.
Is design a subset of linear or incomplete?
It's a subset of linear. It's like a more specialized thing with more constraints. Formally, it means like the parity check matrix of the code is a 4 design.
And what is known for higher number of queries, like 4?
Pretty much nothing.
Yeah.
I'll mention this at the end of the talk, but basically there's very little improvement you can get there. Okay. So for the remainder of the talk, what I want to do is give you some high-level overview of the proof of this exponential lower bound. Okay. And so let me tell you the proof strategy. The strategy is we're going to follow this approach that we had developed in our previous work on LDC lower bounds, which is that we can establish a lower bound for these codes by proving that a certain system of XOR formulas or systems of linear equations, mod 2, are unsatisfiable, and these equations are going to be generated with some minimal amount of randomness. You can think of these equations as essentially encoding the fact that the decoder should succeed when given a code word. And then if we can show they're unsatisfiable, that means there's no encoding map, and therefore there is no code. And so then when we view the lower bounds from this perspective, we can use this algorithm that we've developed in the context of refuting constraint satisfaction problems, and then we can use it to prove the lower bound. And I should mention this application of this algorithm is not black box. So we really do need to open up this algorithm in quite some detail and use the techniques. But the techniques we developed here are pretty general, so it's not too unreasonable for them to actually work in this other setting. And I want you to think of this as some sort of theory analog of this very cool paradigm that the SAT solving community uses to prove theorems. So the SAT solving community has done this really cool thing where you can take a theorem and encode it as a SAT instance. And in their setting, their theorem is usually like some finite set of finite size SAT instances. And then what they do is they just feed it into a supercomputer and run one of their SAT solving algorithms to see if it can prove the theorem. And they've actually managed to prove quite a few very cool results in this way. And so what we're doing here is some theory analog of this. Our approach is definitely inspired by the success of this approach in practice. And essentially, the reason we can't use just an actual SAT solver is because we're doing this for an infinite family of asymptotically large instances. So we have to use a theory algorithm. We can't write code, but I mean, the high-level approach is actually still inspired from this and indeed works. So for this talk, I am actually going to go through the proof not through this lens, but through the lens of presenting the ideas as a reduction to a two-query locally decodable code. And unfortunately, when you go to this reduction viewpoint, most of the intuition I have for the proof pretty much goes out the window. Most of the intuition I have comes from the spectral or like the random matrices you construct here and computing eigenvalues and eigenvectors. But for a talk, this is, I guess, a simpler thing. It requires less notational baggage and so on, so it'll be easier to present the ideas. Okay. The picture is all clear? Okay. So before I can get on with the proof, I have to first explain some combinatorial form for linear 3 LCCs, which is essentially the starting point of all the proofs. And you can think about how the decoder is going to decode x sub u. And basically, for a linear code, you can assume the decoder is non-adaptive. So what it's doing is it's querying some entries of y, some entries c, and then it should compute some predicate on c, and that will determine x sub u. Okay? And for linear codes, it's not hard to imagine you can assume that the predicate is linear. And the more interesting thing is you can assume that these query sets form a matching. So it's going to be a hypergraph matching. So these sets are of size 3 because we make 3 queries. And they will be disjoint. So if I just put this as a picture, I can imagine like here's my code word. And these are the possible query sets in a particular hypergraph h sub u. So I got one hypergraph h sub u per bit in the encoding. And the decoder essentially just picks a uniformly random hyperedge here. Let's say it picks C1. And then it reads the 3 bits, which are here as 0, 1, 0. And then it outputs the parity, which is 1. Okay? So you can assume for linear codes that the decoder has this very, very nice form. And as you can see here, this is a matching because each bit of the encoder or of the encoding is in only at most one hyperedge. The matching need not be perfect, so some of these bits are uncolored, but it's going to be some omega n sized matching, so like most or like some constant fraction of the bits belong into some hyperedge. And you can view this as saying that the parity check matrix of this code is some 4 sparse matrix where basically these equations give you the parity check matrix. So for each choice of u and each hyperedge c, I then add this constraint xv1 plus xv2 plus xv3 equals x sub u for all code words x. And this is my parity check.
Can you assume that they're disjoint?
Yeah, so this is this follows from a fairly simple like generic reduction. It's not very hard to see. Yeah. Basically, like if you're querying some bit too many times, it could be corrupted, and then there must be some set that's disjoint from that you're still using to decode, and then that's how you extract the matching. It's a very like straightforward argument. Other questions? Is this all good with this? Okay. So we now start with this parity check matrix viewpoint of the 3 LCC, and our goal is to construct a 2 LDC, and the length of the 2 LDC will be n to the order L. Okay, and L is going to be some parameter that we'll choose, and so then when we apply a 2 LDC lower bound, we get a bound of k is at most L log n. That's what the 2 LDC lower bound tells us. And hopefully if we can take L to be, say, like log n, this would be log squared, and then I would take like square roots and exponentiate, and I would get like I guess n is at least 2 to the square root k bound. And more generally, if I get anything polylog here, I will get something exponential. So the 2 LDC encoding, so I have to tell you how to build the code. And the encoding map is going to be very, very simple. I just take a code word x, and I'm going to lift it to some y in a larger space, big N, which is going to be n choose L. It's the same L here and here. And I mean, I can identify this with subsets of n of size L, and I just use basically like the direct sum encoding. I take, for each set S, I set y sub s to be just the parity of the bits in S. Okay, very straightforward. The real question is, why should this be a 2 LDC? So that's going to be the main part of the proof. And to show that it's a 2 LDC, I need to exhibit matchings, M1 through Mn, on this larger graph with these vertices of size omega n, such that if I have an edge in this matching, which the vertices are now these sets S and T, it should imply that ys plus yt is equal to xu for all code words. So in other words, this like st edge induces one of these like parity check equations from your matrix, or some, maybe not a equation in your parity check matrix, but some equation in the dual code, and then that's what you use to decode. So if you think of this as like a locally decodable code, your 2 queries here are S and T to Y, and then you can recover X sub U from this. So I'm now going to define a graph and try to show it has a large matching, because that's like the whole rest of the proof. And so I'll put an edge ST if this equation is something in the dual code. And to show that this graph has a large matching, there's one thing I need to show, or at least one thing I need to show. I first need to show its average degree is somewhat large, because if its average degree is small, then, well, you just simply do not have enough edges in the graph to even find a matching of some like linear size, right? I need average degree at least a constant to get a matching of linear size, because the matching has at least omega n edges in it. Right? So if the graph is fewer than omega n edges, I'm already doomed. Okay, well, let's suppose I could make this step work. Then what should I do? Well, if the graph has bounded maximum degree, then just this greedy procedure of finding a matching will actually produce a matching of size omega n. Okay. And the real issue is this graph will not have bounded max degree. This will be false, and I mean, it's kind of inherent to this whole direct sum encoding that this will indeed be false. But the key technical part of the proof is that we can do this row pruning step. We can find a dense subgraph in G sub U, which has roughly the same average degree, but now does have bounded max degree. So somehow this G sub U graph, as we'll define it naively, will have some degrees with very large degree, or some vertices with very large degree. But these vertices will be very, very rare. And so the typical part of the graph will actually just have bounded max degree, and it'll suffice to use this for the whole rest of the proof, which then gets us the matchings that we want, and then we can apply our lower bound and so on, and we'll be done. Okay. Is the approach clear? Okay, so let me now explain how to construct a graph with large average degree. So we have some edge S and T, which tells us that the sum V in S xv plus the sum V in T xv is equal to xu. Notice that if V appears in both S and T, it's just going to cancel with itself. So this sum is just equal to the sum of v in the symmetric difference, which is the vertices that appear in S or T, but not both. Okay? So then I have this equation. And we can view these edges as labeled by a particular set R, which is the symmetric difference. So essentially, what you do is if you have a set R such that this parity check equation is in the dual code, then you get a bunch of edges, which are pairs S and T, for which S, X, or T is equal to R. Okay. Essentially, I can identify each edge. There's a reason for why I added the edge, and it's from this parity check equation that comes from R. And so I can compute for a particular choice of R, how many edges am I going to add? And it turns out that if you go through some ratio of binomial coefficients and do some calculation, the number of edges is like n times L over little n to the size of R over 2, which adds basically this L over n to the size of R over 2 to the density or the average degree. Turns out this is actually not quite the case. This is only the case when R is even. When the size of R is odd, it actually adds 0 edges, and then this adds a lot of technical complications to the proof. But the high-level idea is that this is going to be roughly the density that we'll get, and you can handle the odd case by doing something a lot more complicated that I'm not going to get into. So now let's recall. We started with a bunch of parity check equations. So why don't I just use them here to define these edges? So I can take simply start with the hypergraph HU and look at all these parity check equations for C in HU. These are size 3 parity check equations. I have omega n of them. Okay, now I can just go through this calculation and see what L I need to choose to make my average degree large. And so the number of edges is going to be like this L over n to the 3/2 times omega n, because that's the number of of check equations that I have. And then this tells me that I need the degree, the average degree, to be like L over n. It's L over n to the 3/2 times n. I need this to be at least 1. And so if I set L to be n to the 1/3, this is going to be at least 1. And then if I go through my lower bound, I'll get k is at most L log n, which will be like some n to the 1/3. And this is essentially the heuristic calculation, which tells us the reason why we get stuck at n to the 1/3 when we're doing LDC lower bounds. We just use these naive parity check equations that we started with, and we don't do anything more with the equations. And then if you plug them into this graph, this is what's going to pop out. So the key idea that we're going to do in the LCC setting is we're going to use all n of these hypergraphs to derive more check equations. And when we derive more check equations, the size of the set R is going to grow. So we're no longer going to have the constraints of arity 3. But this is going to be OK, because we'll produce so many more constraints that when you look at this trade-off between the density versus the number of constraints is going to break in our favor, and we'll be actually able to take L smaller and thereby get a better lower bound. So this is the sort of main core technical idea of the proof. So I'm going to go through this next. So the idea is to chain the constraints together as follows. So I start with some equation that I like to write like this. I have some u that I start with, and then I pick a hyperedge v1, v2, w in HU. And then I just get this equation here. So I'm going to think of w as being somehow a vertex that we assign to be special. And now that I've assigned w to be special, there's a fairly natural thing to do. I can just take another equation from the hypergraph HW, which is some equation xv3 plus xv4 plus xw prime is equal to xw. And now that I've written these two equations together, it's sort of obvious what I'm going to do next. I'm just going to add them together. And I get some new equation. So derived from these two initial constraints that we had. And it's of the form xv1 plus xv2 plus xv3 plus xv4 plus xw prime is equal to xu. It's therefore got arity 5 here, right? So the 3 went up to 5. But the number of constraints we have is now n squared. And let's see why that is. Remember, these hypergraph matchings of size omega n. So I have n choices for this edge here, or this constraint here. And once I pick that constraint, I have some constant number of choices for w, the special vertex. And once I choose my special vertex, I again have another omega n choices here. Right, so that's going to be n squared. And now I can go through the calculation here. So the hypergraph produces this L over n to the 2.5 times omega n squared. So this is L over n to the 5/2. And then the omega n squared is this omega n squared edges, or rather to the average degree. And you can just compute this, and the n squared, and there's an n to the 2.5 down here. So I'm going to get L to the 2.5 divided by square root n. And it tells me that I can hope to take L to be like n to the 1/5. And then that will give me a lower bound of k of n is at least k to the 5. So at the very least, we got some small win. We beat k cubed. It's not, some nice exponential lower bound, but at the very least, we've done something non-trivial here. And I want to stress that this is really a heuristic calculation. There's that second step, the row pruning step, that's going to determine whether this will actually turn into a full proof. And that step is like the real technical meat of the proof, which requires some non-trivial combinatorics. But you can imagine here that I've done one of these derivation steps, and I got some small win. Like what am I going to do next? Well, what if I just repeat this process? So I can form longer chains by just basically starting with this chain and then just keep adding more and more constraints at the end of it. And I get some new hypergraph, which now has like omega n to the r constraints in it. The arity, unfortunately, of all these constraints is going to be 2r plus 1. And that's because each of these links in the chain has these two variables that are uncanceled, except for the last one, which has this like extra red vertex. Okay. Unfortunately, this is always odd. And I said that the odd case actually adds a lot of technical complications to the proof. But OK, I mean, we just have to deal with it, I guess, because that's just what this process is going to give us. There's no way around this. And so you can now go through this calculation. We've produced this L over n to the 2r plus 1 over 2, which is r plus a half, times n to the r. And roughly, you can see that this n to the r and this n to the r plus a half almost cancel, and I get L to the r divided by square root n. And now this says that I can take L to be n to the 1 over 2r. But r is a parameter of my choosing. So if I just set r to be like log n, then you can almost imagine this is taking L to be constant. But there's really some hidden polylog factors here. Plus, this row pruning step has some complications that means our final bound gets to be like k is at most log 8n. And then this is our big win. We get this exponential lower bound. Okay. Is the chain idea all happy with this? Okay. So I've essentially justified this step. If I want to make my graph have large average degree, I just form these chains. And then those are the edges I add to my graph. And we've implicitly argued that this means that the graph, when L is polylog n, will have very large average degree. And so then, at the very least, we can hope for there to be a large matching. But to show that it has a large matching, we still need to get this row pruning step to work, which is to say that we need to find a dense subgraph with bounded max degree. So this is really the main technical part of the proof. And this is the part of the proof that I'm going to discuss next. So the key strategy we're going to do is that we're going to show that a random vertex does indeed have bounded max degree. So if a random vertex has bounded max degree, then it has this with high enough probability, I can just discard all the other vertices, and I still will have kept most of my edges, and I'll still have a dense graph. And when you view it through this lens, this means that you can now apply concentration inequalities, and you can use so I guess this is a strategy, and you can now apply these concentration inequalities and use a lot of interesting tools from probability theory to get these bounds. And so the tool we use is this Kim-Wu style concentration inequality, which is a really cool concentration inequality for low degree polynomials in variables where the variables are random with like Bernoulli P random variables. And essentially what's going on here is the degree of a vertex S is a low degree function of the variables that are like the indicator variables of whether V appears in S or not. So that gives you n indicator variables. If you pick a random S, they're roughly Bernoulli P, where P is L over n. And then we can apply this Kim-Wu style concentration inequality to conclude that this polynomial has good concentration, and therefore the degrees also have good concentration. And this proof is essentially some form of a high moment method, and it loses a few log factors, which is why we at the end need L to be at least log to the 5n. It actually turns out that I'm lying to you here. This proof doesn't work. There's some problem with the hypergraph that if there are some things called heavy pairs in your hypergraph, this is actually just going to be a false statement. And then we have to do some other combinatorics thing to handle this case, which adds some extra log squared factors. At the end of the day, this is a log to the 5, this is a log squared, and then the final log is coming from the LDC lower bound, which you might recall was L log n. So that's the last log. And when we view this row pruning step via this probabilistic lens, the idea of Thal's paper can be rephrased as essentially saying that you can just use the second moment method rather than these higher moments. And if you use the second moment method, you only require L to be like log squared n. So then you save quite a few log factors. It turns out that he also has a different way of handling the heavy pairs that saves a log factor. But it turns out that actually we realized later that our log squared here loss was actually just us being a little bit sloppy. And we could also get rid of this by doing Cauchy-Schwarz in a little bit of a better way. But in any case, this log squared is a really big gain over this log to the 5. And so this is how Thal gets his log to the 4. I think it's a very, very cool idea. And then finally, how do we get down to this, like the tight bound for designs? Well, if the parity check matrix H or the hypergraph is a block design, it turns out we can take L to be log n. We don't need log squared. And this is actually not immediate. So it's not just we've assumed something stronger here, which means that if you go through this proof here, you'll get a better bound. It turns out that you actually do need to modify the graph G sub u necessarily. And I think the interesting thing here is that it tells us where the log factor loss in Thal's proof comes from. Because from our perspective, it was not immediately obvious if the log factor should come from this L parameter here, and we can take it down to log n, or if somehow the extra log factor from the LDC lower bound is not necessary. The extra log factor from the LDC lower bound has some deep connections to matrix Kinshin inequalities and things like shaving off this last log n and some other combinatorics results. So we suspected that that was actually the place where the log factor loss was coming from, but it turns out that no, it was actually, we could do a better graph in the design case. So I think this was somewhat interesting. Okay, but that's essentially the proof, right? We construct this 2LDC encoding. We show that there exist these matchings by forming chains to define the edges of these graphs. And then we do this row pruning step to argue that these graphs have very few vertices of high degree. So let me just end by talking about some open problems. The first is this Kleem asks, what happens for larger Q? And you can compute this degree heuristic, and it gets you some small improvement. It's like you can take L to be n to the 1 minus 2 over Q minus 1, whereas for LDCs, you get stuck at this n to the 1 minus 2 over Q. And this is essentially like plugging in Q minus 1 into the LDC lower bound. But this is a very small polynomial improvement. This is not a big improvement. And at some level, the fact that we're getting an exponential lower bound for the 3-query locally correctable codes can be attributed to the fact that we have a very good lower bound for 2-query locally decodable codes. But when you go up to 4 queries for LCCs, you're now going down to a 3-query LDC. And for 3-query LDCs, our best bound is this k cubed, which is just probably very far from optimal. So presumably, this can help you get better lower bounds for LCCs, but you would need to do the LDC problem first.
If you assume something about 3-query LDC lower bounds, can one get a statement for LCC?
I think so. So I think our techniques can be used to give an honest reduction from like a q-query locally correctable code to a q minus 1 query locally decodable code. At some level, that's what we actually did for 3 to 2. For larger Q, this becomes a lot more technical, and I guess we just didn't feel like, if we don't have the LDC lower bounds, it's maybe not worth spending a huge amount of effort on this problem. We should probably first get the LDC lower bound and then come back. But I think it is very believable that we can get a real reduction from Q LCCs to Q minus 1 LDCs, especially when Q is odd. When Q is even, it's maybe going to be more complicated. Yeah.
And for larger Qs, do you believe we can get better reduction? So if you say Q is 10, can we get to the 8 LDC?
I don't think so. I mean, I wouldn't say it's impossible, but at least the strategy we're doing would only go from Q to Q minus 1, I think.
Where does the parity of Q come in? Like, why is it easier for?
So it comes from the long chains. So here the arity is 2r plus 1. This 2 is Q minus 1. So essentially, if Q is odd, then you have an even number of vertices contributed by each link. And this means when you form your graph, what you do is you're sort of splitting evenly these vertices across the rows and columns. And that's something you really want to be able to do. And when it's odd, you can't do this. And this is sort of the reason why odd arity things become very complicated and hard to handle. The sort of natural matrix doesn't exist because odd number is not divisible by 2. All right. So you can also ask, what do we do for nonlinear codes? And essentially what we do is we form these chains adaptively by invoking the decoder, which is now potentially adaptive. So with the adaptive decoder, it first makes 2 queries, and then instead of having it make the 3rd query, we're going to invoke the decoder for that 3rd query, and then just repeat. And this forms a chain in a similar way. There's an annoying thing where it loses the success probability. It'll go from 1 minus epsilon to 1 minus r epsilon. So this prevents us from taking very long chains. Another thing is we can't actually use standard reductions to get to nonlinear codes with this chain strategy. We really need to form the chains first. And then when we form the chains first, we write the decoder as a polynomial. This gives us a really big polynomial for this chain decoder. And then we can refute that using the CSP refutation. And here we really do need the full power of the spectral refutation. We cannot get away with like combinatorial reductions to 2-query locally decodable codes. We really have to use the CSP refutation framework to get anything for nonlinear. And I want to return to this conjecture that I had earlier, that Reed-Muller codes are potentially optimal linear 3 LCCs. And we've proven this essentially in the design case up to this 2 root 2 factor in the exponent. And Omar and Venkat have essentially almost proven this for general linear 3 LCCs. They just are up to this log k factor, root log k factor in the exponent. And as I mentioned, this is perhaps inherent from this rainbow cycle bound problem. And I think it would be very interesting to understand that problem. Well, I mean, that's a very complicated combinatorial problem, but it would be very interesting to understand whether that is really, really necessary or not. Because if it's not necessary, then presumably by turning the crank a little bit more on that problem, you can get rid of this loss and then get the optimal bound. But if you can't, that sort of proves that there's this inherent barrier here. And potentially this approach where we do the combinatorics directly and get this weaker notion of a rainbow cycle can allow us to get all the way up to the square root k bound. But I think the more interesting open questions are, can we get exponential lower bounds for nonlinear codes? Because we have them for linear codes, and our techniques for nonlinear seem to be a little bit stuck. And finally, can we beat this k cubed for 3 LDCs or 4 LCCs, even for linear codes? I think these are both very, very interesting open problems, and our techniques here don't seem close to handling either of these. I think for this problem, if you wait probably like 4 or 5 months, this will probably get solved. Whereas for these problems, they look to be substantially more challenging. So I think this is probably a good place to stop the talk. Yeah, thanks for listening. If you have any questions, you can talk to me after.
More questions?
If you have like some maybe a little bit more relaxed question, like instead of asking like for general LCCs, you assume that your code has some nice symmetry and stuff like this. Can you like get benefit from this kind of? So, for example, your code is like your code is doubly transitive.
I've tried a little bit, and I haven't gotten anything, but I haven't like tried that hard. I think Gopi, you probably had a paper on something like this, I remember. Yeah. So some form of symmetry, you could get some very good lower bounds.
If it's a final variant, then what?
If the code is at finding variant, then you'll get exponential. I think Reed-Muller codes are basically optimal.
Yeah. So if you assume some algebraic structure, you can presumably do better.
Well, let's thank Peter again. I believe that now it is the long lunch break / collaboration break, and we will resume at 2 p.m. Is that right? 2 p.m.